Okay, it is Friday. Good to see you. Bright and early here, eager to get through chapter 7, is it? The rest of the story, SN1 coming up today, and we'll do a lot of examples and comparisons between SN2 and SN1. Just one little number difference between those two designations of the mechanism, but a world of difference comparing the structures and the conditions, the reagents, whether it's a charge or a neutral nucleophile, whether it's tertiary, secondary, or primary. We've mainly looked just at primary and secondary for SN2, but now we'll get the rest of the story. Yeah, so we will finish chapter 7 tonight. So homework 7 is due tonight. Chapter 8 will start on Monday, and that's the rest of the story with the strong bases. We'll do the elimination reactions, the E2 reactions. And it's keeping all these things together that's going to be tricky there for you for test 2. And that starts, what, not this coming Monday, but the next Monday, I think. So you still have plenty of time. Don't worry. Okay. Questions on anything coming up there, business-wise? We just had quiz 4 turned in. We'll get that graded. We'll have quiz 5 next week. I think it's another one on Thursday it'll be due. That'll include SN1 with SN2. And yeah, we'll have had the eliminations by then too. So that'll be a good quiz for you to see, reactivity and how to figure that out. So that's coming up also. All right, so let's go over to the board here. And we talked about this type of reaction before where we compared the primary here with the tertiary. But now we got the tertiary. We got tert-butyl bromide with sodium acetate. We looked at sodium acetate before. That is a charged nucleophile. The solvent in this case is acetic acid itself. And it gives a very good yield for the tert-butyl acetate ester. And the rate here is the different thing, okay? Before with primary and secondary with this nucleophile, we had a bimolecular reaction, okay, with 2 components present in the rate expression. But now we just have the concentration of the substrate, the tert-butyl bromide. It's independent, you see, of the sodium acetate. In fact, here's the other thing. You can leave out the sodium acetate and just do this reaction in acetic acid itself, a neutral nucleophile, right? And look, it's the same rate. You see, it's independent of that. It doesn't matter. So what's the mechanism in this case? Well, we're going to call it what? Substitution still. It's still nucleophilic, but what is it now? It's unimolecular. And it's a hallmark of tertiary and secondary. Secondary is a lot slower. Primary, no reaction with a neutral nucleophile, okay? We're going to see why here from the mechanism, right? So again, it's this hierarchy of thought in OChem, right? Structure, reactivity, what's the reaction, what's the product, what are the conditions, and now mechanism. And hopefully mechanism works in your favor and helps you out here. Okay? Mechanisms will get more complicated, a lot of stepwise mechanisms coming up. But I think as you think about the structures and the properties of the molecules, the mechanism should help you keep track of this, okay? So why is tertiary better and having a neutral nucleophile now making it unimolecular? So let's look at the mechanism. So let's do the whole thing here. So the first step is just ionization. And that might look kind of funny. Well, do these tertiary halides just fall apart spontaneously? Yes, when they're put into a polar solvent. Okay, that polar solvent is nucleophilic enough, it's neutral, whatever. They will fall apart on their own. But if it's in neat form, it's in pure form, you can put that in a bottle, it's stable. Aldrich sells a bunch of these tertiary halides, they're okay. But the first step when it gets in a polar solvent is this step here. And that gives us what? And the bromide, okay. So yeah, why did it ionize that way? And notice how I drew my arrow, right? It's a double-headed arrow, the movement of 2 electrons, right? And if we pull these electrons out of this bond, what do we get? We get a carbocation, and it's a tertiary carbocation. So that's a key thing to notice now. That's different than SN2, where we had mainly primary and secondary things reacting. Okay, what do we do now? Well, how about the next step? Let's just take our acetate in this case, if we have acetate, or we can just take the neutral acetic acid. We'll have to show you that step too. So here would just be the attack there. But look, that goes directly to the product, doesn't it? Okay, there it is. Okay. But notice it is a two-step reaction. We have the initial ionization, and the key here is it's a more substituted halide. So this tertiary carbocation is stable enough on its own in a polar solvent, okay? And we have a polar protic solvent here. We've mentioned solvents a little bit. And then the nucleophile, in this case, it is charged. There is some acetate in there. But this is a very fast step, okay? This is our slow step right here. And that's why we see the kinetics associated with that, right? The rate only depends on the ionization of that. Let's do the thing with acetic acid. So if we have acetic acid as our nucleophile, okay, what are we going to do here? Well, we got lone pairs here, here, and here. There's a couple things we could do. Let's bring these electrons down and use that to attack there. And what are we going to get? We're going to get the intermediate that'll look like this. And what's that? That's just the protonated form of this, right? So how can we lose a proton off there? Well, we can have more acetic acid. Just take that proton off, and we have a deprotonation step. Now that will be typical for the other protic solvents that we'll see for SN1 reactions, where an alcohol or water going on there, we'll need to deprotonate it before we get to the final step. So if we use these neutral nucleophiles that are protic themselves, actually it's a 1, 2, 3 step mechanism. Okay, but I think we've drawn it correctly here. The slow step is still this, right? Okay, this is still fast enough, even though it's neutral, to go on there and form this intermediate elusive proton. We could have drawn this another way. We could have had this lone pair come in and attack, but by resonance, we can actually use that to go directly to this and then deprotonate right there. Okay, if you drew it either way, we'd still give you full credit, but the key idea is this is still protonated upon that intermediate. Don't worry about that. Let's look at another example here. What more evidence do we have for this mechanism? Okay. Now, evidence that we had for SN2 included what? Stereochemistry, right? With SN2 reactions with a charged nucleophile secondary, if we had an R stereocenter, it went to the S, right? We inverted the stereocenter. Now we're going to use stereochemistry again to establish our SN1 reaction. Here's a chiral, an antiopure tertiary chloride. It's got an ethyl, a propyl, and a methyl, okay? So that's indeed a stereocenter, still tertiary. And let's do this in water, okay? And because this is tertiary, it's going to be SN2, neutral nucleophile. That's really more typical, okay? Alcohols and water. And we're going to get the substitution reaction again. But what we're going to get is stereochemistry retained plus the stereocenter, what? Inverted. In fact, it's going to be a 50-50 mix of these two. Now, what do we call that? We better analyze our stereochemistry here if we're using this as evidence here. So what's our top priority group? The chloride, right? Position periodic table. This is the stereocenter. So what do we rotate? 1, 2, 3. So is that S? Everybody agree? Hopefully I won't mess that up. And this one is still S here. And what's this one then? That must be, yep, there's the R. Now, if we get a 50-50 mixture of R and S, what do we call that? Starts with an R, remember? Racemic, yeah. So we go to a racemic product. If we take the optical rotation here, we get 0. It's optically inactive now. Whereas our pure S had an optical rotation. Let's see, it was plus 34. Okay. In fact, you can run this reaction in a polarimeter and put it in water and shine the plane polarized light through it, and you can watch this optical rotation just go woo, right down to what? 0. And that tracks the rate of the reaction. Exactly. Okay. So something's obviously happening here that's different than the SN2 reaction, right? Where we cleanly inverted that stereocenter. We went from an enantiomer R or S to the corresponding S or R, right? And those are both optically active, the starting material and the product. But in this case, the product is optically inactive. If that stereocenter, the one we're talking about, is the reaction that winds up being inverted there. So yeah, so how does this work? Let's look at this. So if we do the mechanism here, what are we going to get to? We're going to get to this. Okay. Now we need to talk about hybridization and why we go to the racemic product, right? This is the carbocation. So the structure of the carbocation becomes important, right? And it is a tertiary carbocation. Notice it's got 3 groups on it. We should say something about the stability of carbocations here. Tertiary is more stable than secondary, much, much more stable than primary, okay? We'll have to examine the structure a little bit. You see, once you get to here, what's the hybridization? Maybe that's the first thing to look at. Our starting material, this carbon right here, is what hybridization? It's got 4 groups on it, so what is it? It's sp what? sp3. Now, how many groups do we have on the carbon where we got the carbocation? sp2, right? And what does sp2 mean? It means we still have an empty p atomic orbital. In fact, let's look at that maybe with a little 3-dimensionality to it. We'd have this, right? So yeah, there's our p orbital that we don't hybridize if it's sp2 hybridized, right? And it's flat, you could say. Top and bottom are the same now. Trigonal planar, right? So what happened to our stereocenter? It went away, okay? It became flattened. This is chiral, definitely, okay? But what about here now? It's achiral, right? Because it's flat. It's got that symmetry now, right in the plane of the molecule. So what's the probability of the attack of water now? Here's our next step. Top, that will lead, I think, to the S that's shown there. But with equal probability, what? We also have the attack from below now, because we have a different intermediate now, right? So that would give the R. By the way, let's finish the mechanism here. So we'd get either one look like that. And you can, put in that stereochemistry if you'd like. Doesn't matter, it's coming from the top of the bottom. It's given both the S and the R. But after the attack of water, it's going to be this. Remember, that's called a hydronium ion. It's kind of like protonated water. It has a pK of -2. It's a very strong acid, so anything can actually take that off. So you're in water, large excess of water. It is the solvent after all. Sometimes these are called solvolysis reactions. Solvolysis is solvent. So solvolysis reactions break a bond and put water on a substrate, okay? So large excess of the nucleophile in this case, that's not part of the rate determining step. This is the slow step right here, right? Loss of the chloride once it gets into polarity. And by the way, how does the water do that? Well, you've got chloride now, carbocation. So what? The partially negative side of water can interact with the carbocation, and what? The partially positive ends can interact with the chloride, okay? They actually form a shell, a solvent shell around both of these, which helps the ionization, okay? So you see on its own, in neat form, in pure form, the halide won't ionize just spontaneously. But once it's in the polar solvent, then it will, okay? But that's the slow step, okay, to go to the carbocation. It's not satisfying the octet. It's only got 6 electrons around it, so it is unstable. But tertiary is more stable than secondary than primary. We need to talk about that too. But are we okay on the mechanism? Let's take that last proton off right there. And you see that will go to the two products, okay? Let's look at the stability of carbocations, a little more detail, okay? So carbocations, we say tertiary, more stable than secondary, more stable than primary. So here I think we've got tertiary carbocation, secondary, primary. Oh, and we ought to add this one. The least stable one is this. That's what a methyl carbocation, right? It just has the 3 hydrogens. So what's the difference here when we have a tertiary carbocation? Why does the SN1 reaction work? Well, the carbocation intermediate is relatively stable, at least in a polar solution. And what is it about this? Okay, there's a couple factors we can look at. One, induction. What do we have here? If we've got alkyls here, these are what? sp3 hybridized. And the carbocation, we already said it, is sp2 hybridized. Which one is more electron releasing? Which one's holding its electrons less tight? Well, it's the one with a lower s character. So inductively, these are actually releasing electrons. And the more you have, the more stable this carbocation is. We call that an inductive effect through the sigma bond framework. 2 is kind of a weird thing, hyperconjugation. Question mark. What do we mean by that? Well, that's kind of a secondary orbital effect, okay? The theory is more recent, but it's well established now. And what it involves is a sigma to pi temporary donation. And let's see, if you have tertiary carbocations, do you have more sigma bonds adjacent? Yeah, and they have to be planar here. Here's one right here, here's another here, here's another here. In fact, if this is tert-butyl cation, you've got what, 3 methyls here? So you've got a potential of 9 carbon-hydrogen bonds that have sigma bonds that have electrons in them. And there's your hyperconjugation effect, right? You can have a lot of these secondary interactions. That'll help stabilize what? A tertiary carbocation if you have more of that. It's not just carbon-hydrogen bonds, it's also carbon-carbon bonds. In fact, any sigma bond will do, can help you out there. There's another factor that can help stabilize carbocations, and we'll see this a little later. I'll do some examples with resonance. If you have an oxygen with a lone pair or a nitrogen with a lone pair, that can stabilize a carbocation as well, okay? In fact, even primary ones, okay? We'll compare some rates there, but resonance, hyperconjugation, and inductive effect. So you see you've got a couple here, right? That's secondary. That can still go under SN1 conditions, but it's slower because it's less stable, the carbocation. And then primary, okay? Primary here, no reaction under SN1 conditions. Why? You just have the 1 carbon here, and this primary carbocation is very exposed, okay? These hydrogens here cannot do the hyperconjugation or the inductive donation, right? They're more electropositive than carbon. So you don't get stable, you get just a little bit here. It's really an additive effect if you have multiple sigma bonds nearby. And then this is the least stable one. In fact, methyl carbocation's never been observed in solution. It's only been observed in the gas phase. But actually, tertiary ones can be made. Let me show you the one here that a chemist at USC, George Olah, won the Nobel Prize for hydrocarbon chemistry, and he established the identity of many carbocations. He used a super strong Lewis acid. This is antimony pentafluoride with tert-butyl fluoride. And this here is very Lewis acidic, so there's an empty orbital there. Forms the octahedral hexafluoro and timonate anion. And what it forms is the stable tert-butyl carbocation. And that is actually stable enough at low temperatures to study it. In fact, he has some crystal structures of some of these carbocation intermediates, and that violates the octet rule. These aren't stable. You can't put these kind of things in a bottle normally. You can't order this from Aldrich. It's an unstable intermediate. We'll see the reaction diagram in a second. But this Olah reaction here actually shows that, yeah, you can make these. And guess what? On the side here in the crystal structure, you can see the hyperconjugation where at any given time, 3 of these are lined up perfectly coplanar, donating in to stabilize the carbocation. So anyway, some evidence there. So it's the stereochemistry and the stability of the carbocation. Let's look at some other examples. SN1 chemistry. Still can do substitutions. If you want to make a tertiary or a secondary, nucleophile going on, use SN1 conditions, okay? If you have a primary or a secondary thing you want to make sure you use SN2 chemistry, okay? Because SN1 will not work with the primary because the carbocation is not stable. Got to use those charged nucleophiles. So here we're using neutral nucleophiles, okay? So here's one. Might look kind of funny there. What would be the product here? Now we're using methanol. Oh, and let's do a cyclic example here that has a couple stereocenters. Maybe we'll talk about this one. So here there's a tertiary thing where the leaving group is, but there's also a stereocenter over here, and we'll do that one with water, okay? So let's just analyze this to see what we get. Tertiary, yeah, polar protic solvent, that'll be good. And what will be our product? It will be the methyl ether in this case, not the ester, okay, not the alcohol. Why? Because we'll get the carbocation. So a little bit on the mechanism here, and then what will occur? We'll attack the carbocation, and then we'll get an intermediate that'll look like what? Look like this. We also call that a hydronium ion. It has a +1 formal charge on that oxygen. And then how do we get to the neutral product? Well, we have a lot of methanol in there. So you just use another methanol. In fact, when we do these solvolysis reactions, the neutral nucleophile is often just the solvent, okay? So it's there in excess, so you can use another equivalent to here. And yeah, the solution does get acidic. Protonated methanol is a byproduct. When we work it up, the neutral ether, though, is isolated by distillation or whatever. But yeah, that would be our product there. We don't need to worry about a stereocenter. This is achiral, right? So yeah, doesn't matter, top or bottom here, same thing, right? How about this one though? Let's see. And with water, maybe let's do the mechanism and see how that might help us out. Would that be our first step? Okay, this is a stereocenter, but it's not anymore, right? It's flat. Now we can attack from the top or the bottom, but look, we still have a stereocenter here. So overall, the chirality of our product's a little bit different. Before we got what? A mixture of enantiomers, right? We just had the one stereocenter where the chloride was. But now we got the 2 stereocenters. We're not going to change this one. That one stays the same. But when we attack with water, what are we going to get? We're going to get the one where the water can be up and the methyl down, plus what? The one where the methyl's up and the alcohol's down. Before we got what? 2 enantiomeric product, it was racemic. Guess what though? This one here, this one is chiral. It has an optical rotation, okay? We can watch that optical rotation change, but does it go away in this case? Will it go to 0? Will it be racemic, this product? No, this one's still chiral, and this one's still chiral. In fact, what's the relationship between these 2 compounds? Not enantiomers. What are they? Diastereomers. Very good. So you kind of have to be careful there analyzing stuff. I don't remember what the optic rotations are of these, but it's not 0, either one. So this will change to a different number. Maybe we'll just say optic rotation equals X here, and maybe optical rotation equals Y here. Okay, but you should see both of these are still what? Chiral. Okay, but looking at the stereocenter, we scrambled that, right? We got top or bottom going on there. Now, some students always ask, well, isn't it easier to attack from the bottom away from this methyl group? And yeah, you may not get a 50-50 mixture here. It may be 60-40 or something. But I'm not having you, memorize a bunch of rules there. Just recognize the identity of these and how it relates to the stereochemistry. That's more of an advanced topic. We'd have to analyze the conformation of this and see which approach would be sterically less hindered. And that's probably the major one, but yeah, don't worry about it. Is that okay? We'll try to keep it simple, but I think the principles carry over here to analyze a trickier problem there. All right, let's go back up to the overheads here, Colin, and see what we need to review here real quick. Yeah, that's on. Okay, so here's our different mechanism. SN1 now, ionization. Here's our carbocation intermediate. Here's the transition state where the bond is starting to break, right? Partial negative, partial positive charge being developed at this high point here. And here's our stable, well, relatively unstable, but stable enough intermediate. I showed you George Olaw was able to isolate these carbocations, okay? So they're not a transition state, they're an intermediate and a stepwise mechanism now, right? And then what? Then we have acetate, or acetic acid going on there, and then down to the product. What do you notice overall? Is this an exothermic reaction or endothermic? Exothermic, why? Because the energy of the products, the sum of the bonds, and the entropy, although we're in solution, so entropy doesn't really matter, mainly delta H, okay? So we're exchanging a carbon-bromine bond for a carbon-oxygen bond. And if you look at the bond association energies, that is favorable. Okay, we did some comparisons there. We won't do it for every reaction, but you can kind of get a feel for why this reaction works, right? We're going to a more stable bond. But how do we get there? So what is the slow step? What's the rate limiting step? Because this is a multi-step thing. It's getting more complicated. Which step is slower? A1 here for activation energy 1 or activation energy 2? Which one's slower? 1. Why? Because it's much higher, right? So it's kind of an inverse relationship. The highest barrier is the slowest step. This barrier is a lot lower here, so it's kind of like mountain climbing, right? The highest pass or the highest peak is going to take you the longest and be the most painful. A more gentle slope or going up just a little bit, you'll be able to get there faster, right? So related to that. And so here's our slow step, and it only involves a substrate, so it is unimolecular. This is a fast step involving the nucleophile, but it's not borne out in the rate expression, okay? So I think that's okay. There are questions on that, though. You should be able to point out, different positions there. Here's the graphic from your book talking about carbocation stability, increasing stability, increasing substitution. The arrows, here's the inductive effect, more alkyl groups on the carbocation, more electron releasing. You can kind of see the hyperconjugation effect here as well. You've got multiple sigma bonds nearby, coplanar with the empty p orbital. You can get more stability. And look, it's just bigger. You're able to diffuse that positive charge over a bigger structure. That's another aspect of the stability. The methyl carbocation, see, it's all blue. That's the positive or the lack of charge. And look, it's such a small molecule, it can't bear that plus charge very well. We can't make those in solution. Okay. By the way, primary carbocation, it's not going to happen. Okay. So no reaction under SN1 conditions with primary. Secondary slower, and the super fast ones are tertiary. By the way, any other factors, resonance that affect that can help that out. Now, this is a so-called Hammond postulate. It sounds kind of tricky, and the wording in the book can be kind of tricky, but anything that affects the stability of this intermediate will affect the height of this transition state leading to it. So there is a connection between kinetics and thermodynamics. I mentioned that. They're not always mutually exclusive. So if you have a more stable, you see, tertiary carbocation, that character is borne out in the transition state leading to it. This is an endothermic step. So the higher thing in energy, closer to the transition state, is the intermediate. So that has more character there in the transition state. The starting material is way down here. It's much lower in energy. Its character is not borne out in the transition state. It's the character electronically of the intermediate, because that's closer to it. If we have an exothermic step, actually, the character of the starting material would be more in line with what the transition state is. But endothermic, and that's what we're talking about here for the ionization, by the Hammond's postulate, if it's less stable here, that will be a higher barrier. If this was primary, if we had a primary one here, it would be another 10 or so kcals per mole higher in energy, and that barrier would be correspondingly much higher. Okay, and so that rate would be super slow. Okay, so yeah, slow reaction, fast reaction. That's what we were talking about with those heights there. Okay, here's a summary of everything. The grand shebang, you could say. SN2. Your main thing here, methyl and primary. Okay, strong nucleophiles, charged nucleophiles, polar aprotic solvents will help do that. They selectively stabilize the cation part of a reagent, leave the anion more exposed to react. SN1, tertiary. And these are the black and white areas. And this is where you want to stay in your understanding. Don't go to the gray area right away and start mixing it all in. You're going to get confused, especially going into chapter 8. We're going to mix in the elimination reaction. Stay with the hallmark black and white areas, okay? Methyl and primary, SN2, and secondary, okay? With a good charged nucleophile. That'll do a clean SN2. It'll be slower than primary, but it's very good there. Well, that's why they break it out here. Secondary kind of being the gray area. Strong charged nucleophiles favor SN2, okay? And yeah, over SN1, okay? So a coxide or a hydroxide. The one tricky one there are the amines, right? Do the amines do SN2 or SN1 mainly? Amines, they're neutral. So what do they fall under, SN2 or SN1? Remember what we said? It's SN2. Okay, those are good enough nucleophiles because they're less electronegative than oxygen, and even though they're neutral, they'll generally do SN2 type reactions with primary, secondary. Tertiary, they'll do SN1, carbocation more stable. And so that's the gray area here. The solvents, the more polar the solvent is, the faster both of them go. But the polar products are better for SN1. The polar aproducts are better for SN2. Hopefully you have a little feel for that. So there they all are. And that's kind of the rub. We can make all sorts of different functional groups now. But you have to focus first on the R group and what that is, and then talk about that. So I'll summarize some more of this, but I want to show you another trickier example first. So let's see this. Let's do this one. This kind of points out this other factor that I mentioned maybe. Let's see if you can get this one. So what do we have here? And this is kind of a gray area one. Okay, so secondary, okay, and methanol. And this takes 12 hours to go. In fact, you have to warm this up. It will go, and it'll form the methyl ether, okay? So, you know, neutral nucleophile, secondary. So what is this? This is SN1, what we've been talking about, okay? It is quite slow. And let's see, here's another secondary one where we have a benzene and an alkene here. This one, same conditions, methanol. This one's done in 15 minutes. Why is it super fast? And what are the products? And notice I said products in this case. You get this product, which is the SN1 reaction, and you get this product. Oh, two products. Oh, and look at that, it's a primary position. How did we do that? Okay, well, we can do our mechanism here for the top one, like we talked about, right? So we got carbocation, then attack with methanol. Then we've got to lose the proton off there. I won't draw that other step. And you can see why that's slow, right? This secondary carbocation, yeah, it's got the inductive stabilization near there. but it's only got the 2 carbons. Same thing here though, right? This is secondary. But let's examine the mechanism, and hopefully that'll help us see why it's faster and why this other crazy product is generated. Can the mechanism help us out here? Yeah, I think so. So what'll happen here? You'll get, by the way, what's pH again? Not the concentration of hydronium ion in water. Little p, little h. What's that stand for? Phenyl or benzene ring there, okay? Maybe we'll draw that out. In fact, yeah, let's do that right here. Let's draw the benzene out. Why is this one so much faster? It's secondary. What else is it benefiting from stability-wise? Resonance, yeah, in a couple spots. We could resonate this way or this way. Which one gives us that second product, though, on the right? It'd be this resonance here, right? So let's draw that resonance maybe. Double-headed arrow, benzene ring, and what? Oh, primary carbocation. Primary carbocations? I just said those are not very stable and we never see them, and that's not how the reaction's going to work. But this is a different type of primary carbocation, isn't it? It's resonance stabilized. In fact, the true carbocation here is this delocalized thing, right? We could draw that fully delocalized. So this is actually the major product. Most of the positive charge is right there. So we can have our methanol attack here, or our methanol can attack here, okay? And then loss of a proton can do that. But it affects the rate. Why does it affect the rate? Well, this electron donation here to get to this resonance here helps push off the leaving group, okay? So we ionize the leaving group more readily there. All right, let's look at some comparisons here. How about a cyclic one again? Let's do, again, a secondary one. Let's start with the cis bromide here. And let's do it with sodium hydroxide in DMSO. And let's do it in water. I'll give you some results here. This one's fast. It's done in 30 minutes. And it gives us what product? This is the trans only. So what type of reaction is that? SN2. Why do you say SN2? It's secondary. It's kind of this gray area. Yeah, it's got a charged nucleophile, right? It's got hydroxide. It's got excess electron density on it. When it collides with this molecule, it's going to want to affect a bimolecular reaction, okay? So it's going to attack from below here and kick off our leaving group. And it's in DMSO, which is helping to solvate the sodium cation and leave the hydroxide more exposed. It increases the nucleophilicity of that, being the polar A product. We just put it in water. It will go. It takes 10 hours. Gives a mixture of this one again, trans, plus what? Plus the cis, okay? And why is that now? We've got what type of nucleophile? Well, we still have an oxygen nucleophile, but it's neutral, okay? So what, SN1 here, SN2 there, okay? Questions on that? I think that's good. All right. Let's do a bunch of examples here now. Oh, we need to mention one other thing first. So how about this? What type of a leaving group is this? It's sp2. It's vinyl. If you put this in sodium azide solution or in water, what do you get? Guess what? No reaction. Same thing there. Why? Well, we could imagine backside attack here, but look, it's got to get in there past these groups. Plus, what's the hybridization here? It's sp2. That's a much stronger bond. Look at the bond association energies. So it's a combination of the attack is hindered and the stability of the bond. And you're not going to ionize it on its own. A vinyl carbocation, by those same reasons, is not stable. So you can't do it at sp2, okay? So keep that in mind. Let's do some reactions in the reverse sense. If you're asked to make this ester, in fact, this might have been an ester we talked about before. I don't think it's the banana ester, although I'm sure this one has a pleasant smell. What if your boss says, I need 3 kilos of that by next week? How are you going to make it? And so this is kind of a synthesis now problem, now that we know some reactions. And this is called a retrosynthetic arrow here, retrosyn. And this lets us plan reactions. Well, what we need to identify is what bond is strategic. What reactions do we know that might help us make this ester, okay? So we'll learn how to make acyl bonds later. We'll even learn how to make bonds here. But these bonds out here would not be strategic, although there are ways to make those. Where's the strategic bond? Right here. So can you apply either SN2 or SN1 reactivity to make that ester? So what would we go back to? And then the forward direction, how do we make it? So we're going to use an SN2 or SN1 reaction. Let's analyze around here. Is this a primary or secondary or tertiary position? Primary. So what type of reaction are we probably going to use? SN2, okay? So let's have a leaving group. And a cheap one would be bromide. 1, 2, 3, 4, 5. Yeah, make sure you count your carbons correctly. And so what do we need to react it with? We need acetic acid or acetate. Which one are we going to do? We've already determined it's going to be what, SN2. So are we going to use acetic acid or sodium acetate? Sodium acetate. Why? Because that will be the charged. Yeah. So we want to use the ionic version here. And we want to use a polar A product solvent. So acetone or DMSO or THF, something like that. Not water, okay? We'd want to use something that's A product, okay? So that would be the correct thing. If you put acetic acid here with a primary, that would be no reaction. We'd have to take off points. And that's just one little hydrogen difference, right? But this is a world of difference. This is the salt. This is the solid salt form. When you put that in there, you can get that reaction to go just fine. All right, let's do some more SN2. What other reactions here? SN2, I'll put a bunch on the board here. And you can follow along here. Potassium cyanide, sodium azide, sodium ethoxide. Oh, and let's put potassium acetylene. Okay, 4 reactions with the same substrate. What are the products? Hopefully you can see this. We'd have this cyanide. Okay, we'd have the azide. And these are primary, so these are archetypical black and white examples for what? SN2, right? And then this one, ethyl ether. Okay. And then what about this one with the butyl and the acetylene right there? Okay, so we just made that bond with the acetylene. Okay, what about with the secondary one? We have the same thing, but with this chiral now bromide. Let's do the same 4 reactions. What are we going to get here? We're going to get cyanide down. Okay, this is secondary. That's with a charged nucleophile, so that's SN2, clean backside attack. How about with the azide? Yep, azide down. Okay, we're exchanging R and S. And let's see the ethoxide. This one's a little bit trickier. We'll see with secondary and ethoxide, they give mainly E2 elimination. But I think of this one, you get quite a bit because it's just a methyl group here that's not too hindered. And then the acetylene, this one I do have to say it will be elimination now. So stay tuned for that. This is just too basic, okay? The pKa of a terminal acetylene is 25. So that's too basic. With primaries, it works fine. With a secondary, acetylenes will do elimination. I'll say more about that later. Don't worry about that. All right, let's look at some more SN1. Got a few minutes here. So SN1, we're mainly talking about tertiary and secondary with neutral, right? So let's review this. Bromide with ethanol. Isopropyl bromide with ethanol. How about cyclic 1 chloride with acetic acid? How about a chiral secondary that has benzylic resonance stabilization? So there's a nice collection mixing in tertiary and secondary. Notice I didn't have any primary. Well, let's do one primary. Let's have the propyl bromide here with water. What's the result of that going to be? Okay, so what would this one be? The tert-butyl would be the tert-butyl ethyl ether. Okay, got that one. How about acetic acid, the tertiary one? It'll be the acetate ester. Yeah, and acetic acid, make sure you know that's that acetyl thing with the methyl and then the carbonyl. So yeah, that's a way to abbreviate acetic acid. So you get that ester. What about this one here? Now this one, how about the relative rates? These would both be fast. What about this one now? Very slow. In fact, I have it 18 hours, but it does go, and it forms that. Okay, why? It's a secondary carbocation now. It's still the ethyl ether. That's okay. What about this one? We've got what, the R or the S here? That is a stereocenter, right? We got the benzene next door. So we do have benzene resonance here. Even though it's secondary, this one's very fast. It's done in 20 minutes, they get this. And what do they get? They get this. They get out the DL or the plus minus version here. That's just one stereocenter, so those are just two enantiomers. We start with which enantiomer here? I think that's that S. Remember, the DL stands for the dextrorotatory, levorotatory one, but they're 50-50 plus minus. So the optic rotation here will go to 0. Okay. And you see why it's faster. If you ionize here, you have a benzyl carbocation where the resonance from the benzene can help you out there. What about this one? Primary. Guess what? No reaction. It'll eventually do an E1 elimination. Mainly, okay? But forming primary alcohol via SN1, no way. If you want this alcohol, what would you react here? Not water, you'd react it with what? Sodium hydroxide. You do the charged one. Why? Because that can really bring it on, right? With a primary, the attack here is not hindered, but the stability of the carbocation is so low that you don't do the SN1. Okay, one more. How about this one? Let's compare the rates of these two. In water. Nope, no, I don't want that. I want just cyclohexyl chloride. What could you say about those reactions? We're secondary. We're kind of in the gray area here. Carbocation. Why would it go through carbocation? Oh, it's in water. Neutral nucleophile. So you don't have a charged nucleophile here. Which one will be faster? The one with the oxygen or the one that's just the cyclohexane? Yeah, this one will be super fast. This one will be slow. Why? Because when we ionize, what do we get here? We get this. Oh, secondary carbocation. But what do we have here? Lone pair resonance can help stabilize that. We get this. But then what do we get to the product? Well, water attacks here, and the product, of course, is the alcohol. Okay. With loss of a proton. Still got to do that. But you see here, we don't have lone pairs that can help stabilize it. So this one's done in minutes, I think 15 minutes. This one takes 14 hours to go. Very different kinetic uh, rates, but they're both secondary, okay? So anything that can help stabilize the carbocation intermediate will help you out there. Okay, so do some comparisons there. I think that's all topic-wise in Chapter 7. We'll mix in the eliminations here in Chapter 8. We'll do the E2 elimination reactions. But again, analyze the structure, analyze the reagent. Solvent, in some cases, plays a significant role. But the main thing is whether it's primary, secondary, or tertiary, okay, and whether it's a charge versus neutral nucleophile. Okay, very good. We'll see you on Monday. Thank you.